Hello everyone. Um, Today we are going to talk about derivatives of logarithmic functions. Also, we're going to discuss number e as a limit at the end of the lecture. So for right now, I'm going to show you how to calculate derivative of logarithmic functions. So basically that's a theorem. And the theorem sounds like this. d dx. You probably remember this differentiation sign. We're not going to use it a lot, but just like a couple of times. I'm going to prove that derivative of logarithmic function is equal to 1 over x. How I'm going to do it? And I'm going to ask you to memorize this proof. It's going to be on the next quiz. Proof. What I'm going to do, guys, I'm going to consider function y equals ln of x. And I'm going to solve it for x. I'm going to take e to the power of y and e to the power of ln of x on both sides. You are going to see why I'm doing this. And we remember cancellation formula tells us if we have e to the power of ln, which are inverses of each other, they cancel each other and we are going to just get x. So I'm going to write down e to the power of 1 equals x. Basically, we solved this equation for x. Now, what I'm going to do? I'm going to differentiate this expression, left and right side, considering that y is not arbitrary argument, but actually a dependent function of x. So I'm going to use implicit differentiation. Implicit differentiation means that I'm going to assume that y actually over here depends on independent variable x. So first I'm going to differentiate the outer function because it's a composition of two functions, exponential function and y of x, which we don't know, let's say. Let's pretend we don't know that it's ln actually. Derivative of exponential function is just exponential function, right? So I'm going to copy e to the power of y. Now I'll need to differentiate my inner function, which is y of x. I kind of don't know what is derivative of logarithmic function, so I'm just going to kind of write it down less. Y dy dx. So literally I'm writing down that's derivative of this y function is a derivative of this y function. Now, equals to derivative of x. X is a dependent variable and we are going to differentiate it and that's going to give us a constant equals to 1, right? Now guys, what I'm going to do? I'm going to solve this equation for dy dx, which is the derivative which I'm searching for, right? What is dy dx? Well, if I divide both sides of this equation by e to the power of y, I'm going to get dy dx. So dy dx equals 1 over e to the power of y. Now guys, I'm going to do one more step. What is actually e to the power of y? I'm going to look actually over here and find out that e to the power of y, sorry, my curve is not really kind of what it's supposed to be. E to the power of y is nothing else than x. So I'm just going to write down 1 over x. And now I'm going to rewrite this expression one more time. I'm going to write down dy dx equals 1 over x. Now, the question, what was y? And let's go back to the beginning of our proof. Y was actually ln of x. So, y was equal to ln of x. So actually what we found a derivative of ln of x. dy dx, it's a derivative of ln of x equals to 1 over x. Kind of, I finished my proof. I'm going to draw a shade square. And guys, I'm going to ask you to prepare this proof for the next quiz. Next Wednesday quiz, okay? This is a kind of good way to prove the derivative of logarithmic function. It's not exactly the same as a book has, but kind of a good way to do the proof. Okay? Now, What is good? Well, derivative of logarithmic function looks very nice, right? We are going to try this derivative on a couple of examples. So example number one, y equals ln of x cubed plus 1. Let's differentiate this function. As you see, it's a composition. It's not plain ln, but instead of x, we have another function x cubed plus 1, which is going to assume that we differentiate a composition. So we first differentiate outer function ln. So derivative of ln is 1 over the argument of ln, right? In our case, 1 over x cubed plus 1. And we multiply by derivative of the inner function, which is x cubed plus 1. We remember the derivative of x cubed is 3x squared, right? Let me put in parentheses. That's x to the power of n. Derivative equals n x to the power of n minus 1, right? Everyone remembers the power derivative of the power function. Okay, so good. So we went over derivative and one example. Now, guys, maybe we do one more derivative as example, and then talk about like integration instead of differentiation. So example number 2, y equals ln of sine of x. Again, composition, but slightly different. And again, let's try to figure out derivative. Derivative of ln is 1 over argument of ln. Argument of ln is the whole sine of x. So we're going to write down sine of x here in the denominator. Now we'll need to differentiate the inner function, and derivative of sine, as you probably remember, is a cosine. Come on, my pen stopped writing. And I don't know why. Oh, okay. Sorry. Something goes wrong over here with it. Cosine of x, right? Well, we can try to simplify a little bit this formula. What is actually cosine over sine? Cosine over sine is cotangent of x, right? So actually, derivative of ln of sine of x is equal to cotangent of x, right? You probably, if you think opposite direction, like, okay, if a derivative of ln sine of x is a cotangent of x, then integral of cotangent, which is inverse operation to differentiation, is supposed to be ln of sine of x, and you are going to be absolutely true, except like plus a constant. Okay. Okay. Okay, guys, we are going to continue, and our next step is to learn how to integrate, right? We know that derivative of ln is equal to 1 over x. Is it true that integral of 1 over x dx is going to be ln of x? It's almost true, with one little detail. Remember that ln of x is a function inverse to exponential function, right? We didn't do the graph last time, but I'm going to try to draw that. So exponential function looks like this. This is e to the power of x. Remember that derivative of x, that inverse of the function is symmetrical over the line y equals x. In our case, it's going to look like this, right? That's going to be a ln of x. As you see, that's an inverse, right? As you see, ln of x is defined only for x's greater than 0, right? And has also limits. Limit as x approaches 0 plus of ln of x equals what? Negative infinity. And limit as x approaches infinity of ln of x equals, well, basically infinity, right? So For us, it means that this formula is going to work only for positive axis, right? Because ln itself is defined only for positive axis. Is it going to work for negative axis, or what is going to work for negative axis? Let's consider this as a problem, okay? So what I'm going to do, guys, I'm going to remember that integration and differentiation are kind of inverse operations, right? Basically, antiderivative, it's a function you differentiate to get your original function. So now what I'm going to do, guys, I'm going to show you what is derivative of the next interesting function, ln of absolute value of x. What is going to be a derivative of this function? I'm going to differentiate this function. So let's kind of first open what is absolute value of x. I'm going to write down ln of absolute value of x equals, well, when x is positive, it's going to be just ln of x, right? When x is positive. But when x is negative, absolute value is going to strip the minus from x, and it's going to place actually x with opposite sign over here, right? For example, if it's negative, if x equals -1, it's going to be just ln of 1, or ln of minus minus 1. In our case, kind of, we have function different on two different intervals. When x is greater than 0, it's ln of x. When x is less than 0, it's ln of negative x. And when x is equal to 0, ln of x is undefined. It does not exist. This ln of absolute value of x, right? Now, let's differentiate it. To differentiate it, we are going to just differentiate this curly bracket. So, for x greater than 0, we remember that ln derivative is 1 over x as x greater than 0. What is going to happen for this one when x less than 0? When x less than 0, we are going to differentiate a new function, ln of minus x. I'm going to use a composition rule. First, I'm going to differentiate ln and write down 1 over argument of ln, right? Second, I'm going to differentiate inner function, which is minus x. And when I differentiate minus x, I'm going to get minus 1. X is less than 0. And if I cancel minus from here and here, I'm going to just get 1 over x. So actually, derivative of ln of absolute value of x is 1 over x when x is greater than 0 and 1 over x when x is less than 0. So actually, it's just 1 over x. It's undefined when x is equal to 0, but where x is greater or less than 0, it's just 1 over x. So if derivative of absolute value of if derivative of ln of absolute value of x is equal to 1 over x, means that integral of 1 over x is going to be equal ln of absolute value of x, right? Plus a constant, because we are looking for indefinite integral. And of course, I forgot to write down dx over here. Now I'll need to erase the equal sign. Yeah, somehow it doesn't work. No, I don't want this. I don't want this square. Let's eliminate it. I wanted to just do eraser. I wanted just to put dx over here. Sorry. Oh, which is almost what we had originally, right? But originally the formula was working only for positive x. Now, for negative x, it's still going to be the same ln of x, just absolute value of it. So ln is not going to feel any difference because absolute value of x is always going to put a positive number under ln, and we are not going to violate any domain of ln of x. Okay, so that's a derivative, or that's antiderivative of logarithmic function. I'm going to consider an example. So my first example, or because we already had two examples, maybe it's example number 3, is going to be integral from 1 to 2 of 1 over x dx. So what I'm doing a definite integral. Remember, definite integral is using Newton-Leibniz formula. So we do antiderivative, which is going to be ln of absolute value of x, and then do substitution of 1 and 2, which is going to be ln of 2 minus ln of 1. You guys probably remember that ln of 1, especially if you look at this graph, this one, ln of 1 is equal to 0. That's erase e to the power of 0 to get 1. So this one is equal to 0, and we just have a ln of 2. That's going to be the area under 1 over x from 1 to 2. I'm going to draw a little picture just to kind of show what physically we're integrating while we are doing this. This is 1 over x function, right? And imagine somewhere here is 1 and somewhere here is 2. Right now we found this area and equals ln of 2. Okay, sorry, forgot to label my axis with y and x and 0. But that's going to be the answer. Now, of course, usually no one is going to give you just to integrate ln, just 1 over x. Maybe sometimes you are going to have more complicated function. My next example is evaluate the integral x over x squared plus 1. This integral does not look like anything connected to ln, right? But if you think that, okay, if it's 1 over x, then what is my x? My x actually here is x squared plus 1. So I'm going to use a substitution. U equals x squared plus 1. Then what is going to be my du? Du, differentiation of x squared is 2x dx, right? And if I compare my du to expression on the top over here, I see it's almost there, just I have extra 2 here. So if I divide du over that 2, I'm going to have exactly x dx. So that's what I'm going to apply, du over 2, because x dx equals du over 2, right? And denominator is u. Now guys, if I move this 1 over 2 in front of the integral because it's a constant, my expression under the integral is going to be exactly equal to 1 over x dx, right? Just in terms of u, which is supposed to give me a ln of absolute value of u. Because u is not my original variable, I'm going to go back to x and write down that it's a ln of absolute value of x squared plus 1. Well, formally, that's a final answer, but you know that x squared plus 1 is always greater than 0. So we don't really need absolute value. And when you look for the answer in your book, doing the homework, you probably are going to figure out that they are not writing down absolute value. They're doing this because the expression under absolute value is already positive, and we don't need to make it any more positive. Okay, so that's how we do integration. Okay. What else do we need to know? Need to learn our logarithmic differentiation. Okay, give me a second. I'm going to record it as a new piece. Okay, guys, so our next topic is logarithmic differentiation. And let me change my color back to purple. Logarithmic differentiation. Okay, guys, I usually teach logarithmic differentiation, a very, very long example from the book. But today I was thinking, maybe we should introduce it on something simpler and then kind of go to that long example from the book. So what is logarithmic differentiation or log differentiation? It's supposed to make our life a little bit easier if we use logarithms. And we don't use it just for fun, we use it in special cases. So normally you use normal differentiation, but in some special cases you use logarithmic differentiation. Special case where we definitely need logarithmic differentiation. Imagine somebody is asking you to calculate a derivative of the function x to the power of x. How are you going to differentiate it? Well, we know how to differentiate power functions, something like this. 3, sorry, not 3. X to the power of 3, right? Derivative of x to the power of 3 is going to be 3x squared. This is power function. Power function argument is changing, the power is constant. We know how to differentiate 3 to the power of x. 3 to the power of x is exponential function, base is equal to 3, and we know that it's going to be 3 to the power of x by ln of 3, right? We learned this in a previous section. Now, this function is neither power function nor exponential, because both are changing. The base, which is x, is changing, and the power, which is changing. So which rule should we use, guys? Well, actually, there is no special rule to differentiate this expression, and I'm going to apply a little math trick. I'm going to take a ln of both sides of this expression. I'm going to use, oh, sorry. So I'm going to use a ln of y, and I'm going to take a ln of x to the power of x. Well, guys, we remember that when we differentiate expression with the power, power can jump in front of ln. I don't want to rewrite everything just because of like my power jumps in front, and I'm just going to write it down like this: x multiplied by ln of x, right? Now, guys, what I'm going to do, I'm going to differentiate this expression considering y as a function of x. So here we have composition ln of y as a function of x, and I'm going to differentiate the right side too. Not difficult. Right side is easy, right? So what is going to be? I'm going to start with left side. What is derivative of ln? Derivative of ln is 1 over argument. Argument is y over x. What is derivative of y? Well, we actually don't know. That's a question. So I'm just going to write down y prime is a derivative of y, uh, which we don't know. So we're just going to cover it as y prime. Now, what do we have on the right side? On the right side, well, that's just a product of two functions, right? We differentiate the first one, derivative is 1, and copy the second one. And then put plus and copy the first one and differentiate the second one. Easy. I'm going to simplify this side. I don't want to kind of rewrite everything, just to kind of change one thing. So we are going to have a ln of x when we multiply, and here plus 1. Very simple expression, right? Now, guys, what I'm going to do, I'm going to, remember my proof of the derivative of logarithmic function. I'm going to solve it for y prime because I'm searching for y prime. I'm going to multiply both sides of this equation by y. And I'm going to have y. Here y cancels, here y is just going to be added to this, multiplied by ln of x plus 1. I'm almost done. Just I'll need to substitute back what I actually have for y. And this is x to the power of x. And guys, if you look at my left side, you see y prime, which is derivative of x to the power of x. As you look at my right side, that's a derivative. So we differentiated it. The trick we used here is called logarithmic differentiation. When people are using logarithmic differentiation, usually, guys, when you have very complicated expression which is produced by products, fractions, powers, and or not very complicated expression, but kind of hard to differentiate it because we don't really know how to classify it. Okay, I'm going to consider one more example of logarithmic differentiation, and my expression is going to be slightly more complicated, but still it's going to work. Let me just change my color. I actually wanted to use a different one. Don't give me. How about green one? Okay. I'm going to use green color. And my next example, and this is probably example number 5, is going to differentiate a complicated function of square root of x e to the power of x squared multiplied by x squared plus 1 to the power of 10. So you see a product of three functions, everything mixed together, a square root and the exponential function, the power function, and the power and the power. So I'll try to use logarithmic differentiation on this expression. Well, what is good about logarithmic differentiation? Your left side is always going to be the same. It's going to be 1 over y prime, if you take a ln of both sides. So I'm going to first write down a ln of y, and here I'm going to take a ln of this expression. A ln of a square root of x by e to the power of x squared by x squared plus 1 to the power of 10. We remember by logarithmic rules that a ln of the product is equal sum of ln's. So I can actually take a ln of a square root of x and a ln of e to the power of x squared and add a ln of x squared plus 1 to the power of 10. I'm going to continue simplifying this expression using rules of logarithms. Now remember, a square root is just it's a power of 1/2, right? So I'm going to write down 1/2 ln of x. Well, again, square root is 1/2, so it's actually to the power x to the power of 1/2, and I'll take it in front. Here, guys, I'm using cancellation rule. ln and e cancel each other. We just have argument x squared. And over here, guys, I'm going to take the power outside. 10 ln of x squared plus 1. We cannot simplify it any further. There is no rule for the sum under the ln. Now, what I'm going to have next. You see, expression over here was complicated expression. Product of three factors. If you use a product rule, we are going to differentiate maybe these first two and then multiply by this and then differentiate each part of it. It's going to give us a long expression. Just to simplify here, we have a sum of quite simple functions, right? So what I'm going to do now, I'm going to copy ln of y on this side just to make sure that the expression is sitting right, the whole expression sits in front of us. Now I'm going to use logarithmic differentiation. So what is derivative of ln of y? It's 1 over y and derivative of y. 1 over y because it's derivative of ln, and y prime, it's derivative of unknown function y, which we are actually searching. What is derivative here? Well, derivative of ln is 1 over x, right? What is derivative of x squared? It's 2x. Easy. No product rule. Right? Here, a little bit more complicated. Derivative of ln is 1 over argument, and we need to differentiate argument, which is going to give us 2x. Yeah, we need to simplify here, right? Multiply 10 by 2, which is going to give us 20, but that's the maximum. So, next step is going to move this y, this one, to the right side by multiplying by y both sides. So we have y prime. Guys, I don't want to, well, maybe I should do it. Multiply y, but I'm going to simplify a little bit. Write down 1 over 2x here, 2x here, and the 20x. My pen sometimes, I think, losing the charge. I'll need to change the battery. So now instead of y, I have to copy initial function for y. We cannot leave it like this because we cannot have like x and y both as arguments. Y is not actual argument. So I'm going to copy the function. Yeah, it's a long function, but still we can see it. So we can copy it. And I'm going to write down y prime equals square root of x e to the power of x squared by x squared plus 1 to the power of 10. And now I copied my big parenthesis with the derivative of the function 20x x squared plus 1. And that's it. I'm done. Okay. Okay, guys. So last thing in this section we're going to cover is a number e as a limit. Return back to my purple color. Number e as a limit. So, well, we remember that we define number e as a number which fits into our limit. Limit as h approaches 0, right? E, well, I don't know, like, should I write down a, then say that a is equal to e when it equals to 1? I'm going to just write down that 1 over h equals 1. So we were actually defining e as a number which fits over here and turns this limit into 1. So if you write down limit a to the power of h minus 1 over h goes to 0. So if you find a for which limit is equal to 1, that's going to be e, right? Well, this is a nice definition which helped us to differentiate exponential function, find derivative of logarithmic function, but not very, let's say, well, we have to be a big computers to find this out, right? We have to just change different numbers, plug them in, and just to figure out number e. There is a little bit less complicated way to calculate number e, which is called a special limit. In math, there are two special limits, and one we learned during our Calculus 1 class, and today we are going to learn the second one. Well, different way to kind of find number e as a limit. I'm going to start with writing down certain functions. So consider function f of x, which equals ln of x. We know that derivative of this function is actually what? 1 over x. Use the theorem, right? We also know that derivative at point 1 is going to be equal to 1. Just you plug in 1 here, and that's going to be 1 here. Okay? Now I'm just going to write down what is derivative of the function by definition. Derivative of the function by definition is going to be derivative at point 1 by definition is going to be a limit as h approaches 0 ln of 1 plus h, right, minus ln of 1 divided over h. Just a standard definition. Just imagine that you have f of 1 plus h, here f. Usually we have x plus h and x, but because we are calculating at a certain point 1, we are going to have 1 over here. Okay? So, next step is going to work a little bit with this limit. We already know that this limit must be equal to 1. Complicated limit, but must be equal to 1 just because we know the derivative of the logarithmic function at 1 is equal to 1. Now we are going to kind of do some calculations on this or simplifying this limit. First, what is ln of 1? Ln of 1, as we know, is equal to 0. So any number and the number e to the power of 0 is equal to 1. So actually our limit is a little bit less complicated. And that's equal limit of 1 over h by ln of 1 over h. You probably will ask me, why did you move the h from denominator in front? Well, I have, of course, something in mind. We can do this because, that's a fraction. 1 over h can be considered as a kind of, if you do multiplication back, you are just going to get exactly the same expression, ln of 1 plus h over h, right? Why I did this? Because I'm planning to use logarithmic rules, and I'm planning to bring this 1 over h into the power of this function. And I'm going to write it down like this. Limit as h approaches 0, ln of 1 plus h to the power of 1 over h. I'll probably tell me like what is it going to give to us. Well, what I'm going to do now with all this expression. I know that this limit is supposed to be equal to 1, right? Originally, or somewhere here, originally derivative at 1 is equal to 1. So it's supposed to be equal to 1. What I'm going to do now? I'm going to raise e to the power of both sides, left side and right side of this limit. So I'm going to write down e to the power of limit as h approaches 0 ln of 1 plus h to the power of 1 over h, a very three-story number, right? And on this side, it's just going to be e to the power of 1, which is just going to be e, right? What are we going to have over here, guys? Both functions, logarithmic and exponential, are continuous functions. So we can actually put this limit outside of like logarithmic functions. So e to the power of limit is going to be same as a limit e to the power of ln of 1 over x. Well, considering the condition that both functions do have a limit and they are kind of continuous functions, well, we do know that they are continuous functions and they do have a limit continuous functions. So I'm going to use here cancellation rule. I'm going to cancel e and ln. And what I'm going to have, I'm going to get a very interesting limit. Limit as h approaches 0, 1 plus h 1 plus h to the power of 1 over h equals e. So, actually, actually number e equals to this interesting limit where h is becoming a smaller and smaller number. Usually, guys, people are going to rewrite this limit in terms of x. So they're going to write down e equals limit as x approaches 0 of 1 plus x to the power of 1 or x. You see, what is interesting about this limit? Well, first, what is the power? Power, when x approaches 0, is becoming equal to infinity, right? What is going to happen in parentheses? While x approaches 0, it's 1. So basically, that's what we have. I'm going to put in parentheses. 1 to the power of infinity. Well, generally speaking, if the power was not infinity, 1 was really 1, not 1 plus some small number, we are going to have just 1. But in this case, in this special case, we are not going to have 1. We are going to have actually e. Interesting, right? 1 to the power of infinity, where we are a little bit not infinity, a little bit not 1, is going to be equal to e. That's a special limit, and we are going to see it during math again and again and again. I'm going to consider just one example to kind of show you how people are using this limit. I don't remember like example, maybe 5. So let's calculate limit as x approaches 0 as 1 plus x to the power of 2 over x. You'll probably ask me, not exactly the same one, right? How do we calculate this limit? Usually, guys, we calculate limits like this, doing some math, substitution, or rearrangements. For example, here, guys, what we are going to do, we are going to represent this limit as 1 plus x to the power of 1 over x multiplied by 2 as x approaches 0. Well, we know that the product of two powers, it's a power and a power. And if everything is continuous, we can consider taking power outside of the limit sign. So we have 1 plus x to the power of 1 over x squared as x approaches 0. And guys, if you kind of compare it to what we have, that's a limit exactly which is equal to e, this limit. And we are going to have e squared. Interestingly, that a very nice, interesting limit is actually equal to e squared. Okay, well, that's very good. Now I'm going to give you the problems which you need to consider at home before you come to class on Wednesday. Okay? Okay, guys, problems to solve or work by yourself at home. You can also work with somebody. So, problem 1, integral of tangent of x dx. Find it out. Integrate. Problem 2, differentiate. Find y prime if y equals sine of ln of x. Number 3, find y prime if y equals, equals x to the power of square root of x, and another y equals sine of x to the power of ln of x. A little bit more complicated. Let's label them as A and B. And the last problem is find the limit. The limit 1 minus 2 over x to the power of 3x as x approaches infinity. Well, that's it. Try to solve these problems at home, and if you have any questions, bring them in class on Wednesday. And I think that's it. And I'll see you all in class. Okay? So, bye everyone.